we talked about measurements. I said, well, if you measure position, you collapse the wave function to a form that corresponds to a particular position. If you measure momentum, you collapse the wave function into a form that corresponds to a particular momentum. Or if you measure a range of momenta, it would be a wave function that corresponds to that range of momentum, the wave packet. And if you measure energies, you collapse the wave function to a form that corresponds to a particular energy. In other words, if you have, for example, a harmonic oscillator, then it will take on the form of one of these psi's, okay, of the harmonic oscillator. If it's a particle in the box and you make the measurement of energy, it's going to take on one of the psi's, the particle in the box modes. And I want to elaborate on that. I want to explain, I want to clarify certain potential confusions here, okay? So in general, you can always express your wave function as a sum of the modes that we've been discussing. In general, you can express can be expressed as, I'm not sure why it's delaying, there's something wrong. I'm going to wait until buffers. Okay. So in general, you can always do that. How do you find these coefficients? That's beyond the scope of this class. We're not going to discuss it. But you can always fine-tune the coefficients to get the wave function that you want. You don't always express the wave function like that, but one can express it like that. If some of the C's are missing, then when you do make the measurement, you're not going to find that wave function. So for example, let's say a wave function is expressed like this: C1 psi1 of x e to the minus I e1 over h bar times t plus C2 psi2 of x e to the minus I e2 over h bar times t plus, let me mix in seventh mode, okay? Plus C7 psi3 of x e to the minus I e7 over h bar times t. Okay, now you perform the measurement. Let me beautify this a little bit. This is kind of a little bit messy. Now you perform the measurement. And I ask you, what are the possible outcomes of energy measurement? There will be only three outcomes, either E1 or E2 or E7, okay? If the wave function does not have E8 in its sum, then you will not get the eighth mode, okay? You will not get the eighth energy, okay? So measure energy, okay? Get either E1 with wave function psi1, or, and I'm leaving space here because I want to discuss probabilities, E2 with wave function psi2, or E7. By the way, this should be 7. You're right. This should be 7. Or E7 with wave function psi7. Okay. You make the measurement. Let's say you got E7. Immediately after the measurement, the wave function will be just psi7, and the particle will have energy E7. And you might say, wait a second, does it mean that your energy is not conserved? No, it means the energy is not known prior to measurement. Once you've made the measurement and you found the energy E7, the wave function will be in psi7, and it will stay in psi7 having energy 7. This differs a little bit from other measurements, right? So I discussed that if you measure position, you collapse the wave function, and then the wave function spreads again, involves. If you make the measurement of momentum, you collapse the wave function, and then the wave function modifies and evolves. When you make the measurement, once you've collapsed the wave function to psi 7, it stays in psi 7. You might say, why? Why such a preference to energy measurement? Because the Schrodinger's equation is really an equation related to energy. This might sound a little cryptic, so just hang on. I will explain that in the next video. But before we get there, my question is, what's the probability that you're going to get either psi 1 with E1, psi 2 with E2, or psi 7 with E7? And the answer is, with probability magnitude C1 squared, okay? With probability magnitude C2 squared, with probability magnitude C7 squared, okay? And I hope you are seeing the pattern. We've already seen this kind of thing before, right? I gave you example of a mixture of two plane waves, okay? So this is, okay, so recall example with plane wave superposition. A e to the I kx minus omega k1x minus omega 1 t plus b e to the I k2x minus omega 2 t. If you measure momentum, you're going to get either k1 or k2. And the probability that you're going to get k1 okay, okay, with probability magnitude a squared or magnitude b squared, respectively. So when you have a discrete sum, such as here or such as here, the square of the magnitude of each coefficient gives you the probability that you're going to collapse the wave function into this or into this. So if you measure momentum, you're going to get either h bar k1 or h bar k2 with probability magnitude a1 squared or a2 magnitude squared. If you have a sum in terms of energy states, like psi 1, psi 2, psi 3, then if you measure energy, you're going to get one of those energy values with probability magnitude c1 squared or magnitude c2 squared. Going back to momentum, this should not be too startling, because another example with a continuous sum, in other words, not discrete, this momentum or this momentum, but a whole band of momentum, a whole spread of momenta, right? So that's called Fourier transform. So instead of a integral, instead of a sum, you have something like this: a of k e to the I k x minus omega of k t dk, and the momentum usually goes from minus infinity to plus infinity, right? And then the probability, density of momentum measurement outcome is magnitude of a of k squared, okay? In fact, you can see why that is, right? Because that's just an example of taking the coefficient of that coefficient in front of the term with that particular momentum and just taking its magnitude squared. you have already known that, right? We've already discussed many times that the meaning of the Fourier transform is the probability density of a momentum measurement outcome. So here it is in action, okay? Okay, you have a homework problem in which you get to practice this just with discrete sums, okay? I'm not gonna go to continuous integrals. We didn't discuss how to actually compute this integral, okay? We discussed the meaning of this thing, and you have already known the meaning of AFK, so that the magnitude squared of momentum, the magnitude squared of the Fourier transform gives you the probability of obtaining momentum in a small range of k's around that particular value, right? And similarly for the wave function itself, you can think of a wave function, when plotted versus space, as really a sum of these peaks. And then it's also kind of a continuous sum of peaks, all placed at different positions. That's why the square amplitude of the wave function gives you the probability that your position measurement outcome will be here. So you see all these ideas are all on the same footing. So if you express your wave function as a sum of wave functions that corresponds to a particular position, and you measure position, the probability of obtaining that position is basically this square magnitude of that coefficient in front of that position. And that's what the wave function is. If you express the wave function as a sum of a wave function that correspond to particular momentum, the plane wave, then when you do measure the momentum, here's a discrete example, then the probability of obtaining that particular momentum, h bar k1 or h bar k2, is given by the square of the amplitude of A or square of the amplitude of B. When the wave function is expressed as a sum of wave functions that correspond to particular energies, then when you make the measurement of energy, you're going to get one of those energies that are in the mix, in this case, E1, E2, or E3, or E7. And the probability of obtaining the energy is the square of the magnitude of that coefficient that corresponds to that energy. You see, so all of these ideas are on equal footing. Your homework has practice, so you will get more comfortable with these ideas.